Yeah, so today we will be actually working with the Astroquery SQL and a light idea of how deep learning works in the field of galaxy classification and spectral classification of AGN. So we will be actually using some methods to classify AGNs types in different spectral values. Okay, so we will be looking that in a few minutes. So I'll search navigator in SDSS. So so this one is not the website I want to go. Okay, just a second. So they don't have a proper website SEO, so I have to just find out the proper link. I have actually not saved it in this laptop. Just a second. So I'll just share this link with you guys. Okay, Supriya, I don't know about that. You can just share the email with me. That is actually logged in with your YouTube account. So I'll add you in all the videos. Assess. Okay. So you can just open this link with you guys. So now, hopefully, it must all work now. Because earlier we were getting an error of the service, right? So I'll just click on this cast job here. Okay, so yeah, I guess it's working now. So when you will go to cast job is a web page which helps you to learn about SDSS query. So every survey provides a query system where you can find the exact table names, columns names for that particular data. Okay, so let's say you have to do an manga query, so you have to go to their profile. So today we will be actually learning about SDSS queries, because most of our AGN data comes from SDSS. However, we use various data sets like Keck observatory, so we have various blizzards one, so we have X-ray astronomy data from different surveys. So there are a numerous of data, right? Data sets from different surveys, but for optical observation we use SDSS. Okay, like I use SDSS. So what I will do is I will go here to the login on my top right corner. So you have to log in your account first to get more details on that page. So you can just create a new account here also. So it will hardly take 2 to 3 minutes. So you can create your account here. What it will be going to show is, you can see here now I have more option on the same website that I was not having earlier when I was logged out. So I'll just zoom it for you here. So there is something called help, and there is something called tools, there is something called query. In the help you will see all the method how to retrieve the database and all the frequently asked questions and some of the example of queries, but these example of the queries are not that much useful. This is just a basic query. So we will be doing something in advance to get a whole bunch of data. So what I will be going to do is I will be going to my database, my DB here. So in my DB, it's just getting load, just a second. You will see these things. Oh, just a second, what's happening? Okay, so you will see these things, my DB view, tables, functions, procedures. Okay, so just a second, I'll click on MyDB here. I think when I'm zooming this web page, it's just showing some errors. Okay, so here you can see your data. So I have just used uh, 1232 kbs out of 5 lakh kbs, okay, 500,000 kbs, right? So that much data I have used, and even I have just downloaded so many files from here, and still this much data is being the storage has been used. So it doesn't matter about that, we have a lot bunch of storage here. So when you will go to view tables, functions, you will see different things, but I have to go to tables. Now it will say nothing found. Why? Because in my database I have not stored any data yet. So we have to go to DR18. We still have DR19 here also with us, but I'll recommend go to DR18 because it is most stable one. Okay, so you will go to DR18 here. Now you can see you have the names of every table here. So most used data for the galaxy survey is gal extra spec, spec extra, gal spec info, gal spec index, and gal spec lines. So these actually give us the data for the flux values for that particular uh, emission line. Okay, so it will give us the spectral values. So we will be using these things here. So when I open one of these, let's say I'll click on gal spec line. So you have to just wait for some few seconds. So it take time to load for a minute. So yeah, now you see it load here. So you see we have sigma forbidden errors. So we have sigma Balmers. What does sigma stand for? It's velocity dispersion. Okay, so I will be explaining about velocity dispersion in tomorrow's lecture, when we will be discussing about AGNs and what is the correlation of velocity dispersion and their masses, and how it is very difficult to measure velocity dispersion for the galaxies like Seyfert type 2 galaxies, where we can't do direct observations. Okay, so these are some of the concepts when we go to the practical and theory part of the agents, the concept of agents. Okay, so that's important if you want to go into the field of agents, because tomorrow it will be a lecture full of knowledge. Then we have these values from oxygen at this particular wavelength. This will be used a lot. Then we have these values, flux values, H delta, H gamma, and oxygen doublet and all that stuff, triplet, H beta, and similarly we have a lot of values, and then H alpha flux you see here. So we have a lot values for different emission lines, absorption spectrum. Now we also have, just a second. Okay, so where does it go? So yeah, we have other things also for galaxies here. So there are something also called photo object all. So it actually provides us the data for redshift, RAN deck, and all other things. So basically not this one, I guess. So yeah, you see it actually provides us the different band values. Okay, so U, G, R, and in different kind of numerical values. Then we have PSF values in that particular band. Okay, so this is actually the error value. So this is the value in that particular value band. Okay, so these are very useful in different ways. So it's not only about those particular things that I only told you, but there are bunch of more parameters that you can actually work upon. Okay, so it depends upon what type of thing you are working upon. Okay, so now you see here, now we can go to this query button here. Okay, when I click on this query, so there are a whole bunch of things here. So you can actually go to this DR18 here, and you can start writing your query here also. So when you will start writing a query, you can also submit or quick. There is a button for quick. What it will be doing is, it will be actually checking your query if it is right or wrong, and before extracting the data, it will actually tell you that it's correct or incorrect, and then it will be going to give you a preview of the data. But when you will submit the data, and if your query is whole large data, a large line of code, a whole bunch of line of codes, what will be going to do is, it will be actually giving you the whole code. If you get any error, you will be stuck. Okay, so you have to find the way to fix that if you are working on a huge chunk of lines of code. But the quick is actually give you a immediately solution for your query. Okay, so we will be not working here. We have some more good interface for this thing. Plus we have a Python version of Astroquery, which is known as Astroquery. For this query, SDSS query, we have Astroquery, in which we can actually merge the SQL code and Python code to write a query and get the data. So without wasting this time on lecture and boring explanation, I'll just get into the hand-on stuff. Okay, so I'll create a new Python notebook of day underscore 7 here, and now I'll create a new Python notebook here, which will be actually day underscore 7. Now we will be writing a Astro query. So before writing a huge Astro query, we will be getting into some simple Astro queries, and also before writing in directly in the Python, we will be writing in the server of SDSS. So coming back to this page, which is the main home page to navigate the galaxies, you will see this thing here, search tool. Okay, in the search tool you will see SQL search, and when I will click on this, you will see you have this page here, which actually have already written some of the SQL code here. So I'll explain this code itself, and we will be getting more and more deeper into this. Okay, so and you can just have option of the output format, which are HTML, CSV files. So we refer actually a CSV format or a FITS format, and then also we have VO tables, XML and JSON files. And you can also directly you see in the cache job there was something called my database, right? So when you will submit and get the data from here, it will actually directly put that data into your database. So it depends upon you, if you are doing a long term research and you want to store every single data set at every single checkpoint. So you can also save that it in the database, which will be connected to your account. So just a second. Okay, so you will get a similar kind of code here. So this is a SQL language code. Okay, so you can see here in the comment section. So you see in the SQL language we write a comment like this, not with the hashtag. Okay, so this query does a table join between the imaging and the spectrum table and include necessary column in the select to upload the result to the science archive server for FITS file retrieval. So basically we have actually both imaging data, what imaging data, basically the band values and all that values, and we have the spectral data also. Now when I will zoom in this, so what the first line of the code says, it says select top 10. What does it mean? It will actually select the top 10 galaxies or whatever the object we want. We have not specified anywhere that we only need a galaxy here. Okay, so we will be doing that in our main long Python file, because we will be doing the classification itself with the same data which we will be retrieving. Okay, so that will be exciting, because now you will be getting a real data and you will be classifying those AGNs with the different methods I will be showing in future. So basically the second line says you need the object ID, p dot object ID. P is just like you can say a index. So basically it is the list name you can say, or a table name, and object IDs are the index names or a column names inside it. So I am just relating that to the Python indexing thing. So what just like we import numpy as np, we assign a short name for these tables here. So we have assigned like from photo object as P. So you see these are written all in capital, so you have to remember that you have to keep them in capital format. So photo object was one of the table there, and these small things were one of the columns inside those tables. Okay, so as P, so from P extract object ID, RA, right ascension, declination, U band value, G band value, R band value, I band value, and Z band value, and these some of the more parameters like filled. Now similarly, if you want to add one more table, you have to write join here, join and then table name. If you want to write a short name for it, also write S. Okay, so and on S best object ID is equal to P dot object ID. What does this mean? This is something new. So it was okay till we defined join spec as S. Now there are some things, maybe when you are extracting the data from spectral object table, you might get different object ID data. Okay, so your object data must not cross match in that case if you doesn't write this code here, which is actually trying to match the exact object ID which we are trying to retrieve in our first photometric data, right. So this line is very important, that on means to overlay our data basically. So S dot best object ID is equal to P dot object ID. So you have to first cross match those object ID, that it should match with each other, and then you have to retrieve the same object ID class redshift as redshift and plate MJD fiber ID. So why I have written Z dot S dot Z as redshift? Because when you will be exporting data, it will be actually making the columns, right. CSV file has columns and rows, so column will have exact these names RA dec. So I don't want to confuse this Z with the photometric Z band. So I have written here that convert the name of the dot Z, which is actually redshift in the form of the spectral here, spectral object here, and you have to change the column name with the redshift here. Okay. Now is basically the conditional values, which is where, just like numpy dot where, when we actually restrict our data between a particular range, similarly we have to write where here. And now I have defined that the G band values and U band values must be between 0 to 19.6 and G band values between 0 to 20. So I don't know what it's trying to extract. It's actually trying to extract some of the random data for those galaxies or stars, maybe quasars, stars, galaxies, or any other artifact also sometimes happens. So I will try to run this data, run this SQL query here. So I'll show you the result. So I'll click on the CSV because we know pandas, right. You can also try for FITS file. But then you will not be using pandas library, then you will be using FITS library, Python package to extract your data. But it's the same, we have learned both. So I'll just click on submit and it will open a new link here, and it will directly give me our CSV file. And when I try to open this CSV file, you see we have these data here. So we actually have to remove the first thing here, first row here, which actually said table 1. So now we have to work on our data. So when I zoom, you see you have different all of these things, and the redshift has been converted to the word redshift here. So I'll cross this. Now sometimes what happen, your SQL query is wrong and you can't be able to generate the data. So I'll recommend first to go with the HTML part. So HTML part is actually for the overview. So when I will click on submit here and I'll go to this again page, you see your SQL command, it will show you all of your thing here, the commands here, the syntax here, and here will be your data files. Okay, so now you can also, okay, so there are some more new options here. Okay, so I also don't know about these files. So yeah, there is also called something vget. So you might also know about this. So you can just vget this file and it will also download these files. Okay, so we won't be using that particularly. But when you will be having some error in your code, so it will be actually giving you error, exact error name or details here on this page. Okay, so you don't need to worry about that. So I'll recommend you to first go to the HTML format, and if your word query run very quietly well, then you can just shift to the CSV and download the data. Now we will be actually going to the main stuff, querying our galaxy data. Okay, so you see here we have different examples here. So if you want to go for the black hole mapper, so you have different options, like you have different queries here. Okay, so you see the class is now defined as QSOs and redshift is defined greater than 3. So you can actually look upon these things. These are very beautifully designed tutorials, basic tutorials to start with. So these are like very good for starting point when you are not guided properly. So you can just look upon these tutorials here, but we will be actually first doing exact query for querying AGN values. Okay, so let's write a query. So what we will be doing is now, so I told you, you can one method is to actually write the query here and just submit here to download the data. So what we will be doing now is we will be working with Python and SQL in the merging form to get the query. Okay, now we will go to our Jupyter notebook. So any doubt till here? I guess it was just simple explanation. I told you how to do these stuff. So do you have any doubt? You can ask. Fine. Okay. So now I'll just close these things here. I'll keep this open to show you in future the query we write, and we'll verify the data. Okay, so now what I will be doing is, okay, I'll just paste this link over here in our this thing. Okay, and I'll just add a new column here, new cell here, and I'll just define SGS query. Okay, so this is the actually link you can get the SQL search here. So now we need some Python packages for our today's work. So we will be plotting in a very good format. So you have to download some Python packages, which is pip install Astroquery, pip install Galamo, and yeah, that's it. These two packages you have to download. So when I will click you will find that they are already stored in my PC. So okay, so it's actually updating some of the Python packages. So maybe some dependency was not new, so it actually updated it itself. So yeah, you can see it actually wanted new numpy update. So yeah, it happened. However, it can work on the older ones. Okay, so I'll just make it this raw. Now there is something called pip show the Python package name. So how does that work? What does that mean? Pip install, instead of install we have to write show Galamo, let's say. So basically you can get all the information about that Python packages, what it does it do, who is the author, who is the actually author's mail, something like that. So let's go for AstroPy first. So you can see the version I have installed is 6.1.7. now it's actually 8th version. And the emails is actually astropy.team@gmail.com. the license it has been shown. So these are all the things, the requirements. It requires these packages. to be installed, but it what actually it do is uh, it actually uh, kind of pre-install it for you when you install. So the summary is AstroPy and the web page is also given. Similarly, when I will write for Galamo, you will see that it's actually my Python package, my group's Python package, well my group here in India. So it is actually a Python package for comprehensive galaxy analysis. So basically what does it do is it actually classify galaxies using deep learning technologies and deep learning algorithms. Right now we have a publication in progress for this Python package, and you can just see this Python package here on this website. So we have a new model here which is trained on decal survey. Decal survey, we have trained those galaxies which are provided by decal survey. Okay, so what we took is what we do is we took the images, we apply some computational knowledge of deep learning onto that galaxy to predict and train a model to predict something new image that comes up to our computer. So let's say you have trained 2 lakhs of galaxies to your computer. So you know that your PC is dumb. Okay, so it don't know what type of galaxy it is. So what in Galamo we have done it, we have provided a bunch of galaxies and trained it that this galaxy is of this type, and if this come in xy dimensions, you have to classify it properly. If it get rotated by some angle, you have to particularly see that if that actually is that galaxy or not. So it is actually work it actually contain more than just deep learning and some or more uh, tutorials and packages itself inside it. So we have currently 3 packages inside it. So most of the time 2 are mostly used, which is for morphology classification and spectral analysis of AGNs. So you can just go and look to the code itself, it's open source. So there are tutorials here on this page also for this Python package, image classification, BPT analysis and low light image enhancement. So first 2 are actually more popular and mostly used by people. So right now we are on the 1.12 version. So the main motive of Galamo is to just provide a very direct pipeline to observatories to for the classification, just like Rubin telescope is just coming up and people are making softwares for it. So it is also one of the initiative for that type of coming up projects. So you can see that yeah, so the mail is actually mine mail. So I was the first author for this project. So yeah, so you can find the code through GitHub. So yeah, so we will be actually using it for the this pipeline. So this Python package for the classification of the AGNs. Okay, so I'll show you how this is helpful, and now you will actually see how Python packages, not just Calamo, but AstroPy and other Python packages reduce our work. Okay, so this is how you can just work on this. So now we will write our first query, actually the second one or the first one you can see. So I'll just define a variable, and since we have to write a multi-line things, so I'll just make triple these things, and I'll start writing from here. And first line must be the same, select, let's say top 1000 of the values, and you have to press tab because all of the that will be inside it. So now I will be writing I dot spec object ID. What is I here? I will be actually gal spec info. I showed you the gal spec info, right? So they contain some of the info. So what I will be writing at the end is from gal spec info as I. Similarly, I will be joining gal spec line as L, and after that I will be writing on I dot spec object ID is equal to L spec object ID, so that it can match the exact object ID. So I dot plate ID. So these are not very much important, so I can just skip this. So plate ID and that things are not that much important right now. So plate, MGD and fiber ID are not that much important, but when you are doing research based on your requirement, you can fetch that. Okay. So dot z, what is dot z? It's redshift. Dot ra, declination. These are important things. Now from the spec lines, from the spectral data, we need actually the emission line fluxes and their equivalent width and their flux ratio, flux arrows, sorry. Okay, and then we will be actually needing a constraint over their flux ratios. I will be showing that. So first I will write a comment here. Now I will be writing emission lines, error, fluxes first. L dot H underscore alpha underscore flux, then H alpha flux, then H beta also, H underscore beta underscore flux. So you have to write the exact name here. Okay, so you can't make any typo error or any capitalization of letters. Okay, because these are actually the same column names in the inside those tables. Okay, so underscore O 3 with 5007 wavelength underscore flux L. Okay, so I did a mistake here, I have to press dot here. L dot, then nitrogen underscore 6584 underscore flux. So actually I have this query already written for me. Okay, so I don't think that I am just writing out of my mind or something. So I am not that much like cramming person. So I have just in front of me this query. So you can actually fetch this query. I am actually following this tutorial of BPT for you guys, because this is actually written by me for the people, right? So I have written this beautiful tutorial here where you can actually get every single info. So I am writing this same query here. Okay, so for the data retrieval, so you can actually run this thing here directly. Okay, so we will be doing these stuff, but before these beautiful plots, okay, so we need to get an beautiful knowledge of classification. So before plotting these, I will be showing you what actually these plot are in the conceptual knowledge. So okay, so this is this might help you by side. So but yeah, you must follow with me so that you can just also practice this alongside, rather just copy paste. Okay, so similarly, so why particularly these fluxes? Why not other elements? Because these are actually the input values of a BPT classification. BPT is one of the diagrams for the classification of AGNs based upon their spectral values. Equivalent width. Okay, now let's say H, we only need the equivalent value for H alpha and nitrogen, because we will be plotting them, you see here. So basically in the formula of Kaufman, and okay, so I will be explaining the concept later. Okay, so just follow up till here. So because if I get to explain the concept, it will mix up all things. Okay, so let's first write this query and fetch the data, and then I will show you what is actually behind that. Okay, okay, so I'll just write the query fastly. Equivalent, then nitrogen doublet underscore 6584 underscore, okay, then flux error. So it's a big query. Okay, so it's actually a thing you can actually work upon, and it's a real query for querying the AGN data. Okay, so you can actually use it multiple times in your research. So it's a journal query for the data for AGNs. So it's very useful. This query is actually very useful. So you can use this multiple time in your research, rather writing it again and again or asking any other AI model to do that for you guys. So what I will just do is, since we need these all values, right, I'll just copy this here and I'll just paste that here. Okay, and just I'll write error here. We have got this, then we have got error here, and then we have to actually add one more thing here, which is o singlet 6300 underscore flux underscore error, and I have to add this here also somewhere. You can add, so it doesn't depend that you have to go in this chronological order or this order, so you can just write anywhere. It's not like just I have write the width here, then I have to write the error. So you can actually mix up these all things. You can write flux and then flux error and then equivalent width or something like. So this can be anywhere. Okay, so just to make it very cleaner look, I have just given this type of thing here. Now I have to just write from where. From gal spec, so the spec s is in capital as I join gal spec lines as L on I dot spec object id is equals to L dot spec spec object id. So you see why I have this done here, to match the spectral spec object id, so that it doesn't give some other type of data set. Okay, so now I will have to write where it will be I dot z. Now between let's say 0 to 0 and 0.3. So I am just writing the same tutorial part, so I have already written it for you guys, so you can just look up on that, because that's the standard method of query, right? And it's a very general query for AGN, and I don't think that's either a weak query. It's actually a very well defined query here what we are writing. Okay, so H alpha. So what I will do is, so as you know, I'll just copy this query, because we have a bunch of ratios. So you can come to tutorial and do this thing here. I'll just copy this query from here, from my tutorials. So you can just go to my this website, a Glamo website, and copy this thing here. So you see it's a quite bunch of code. Okay, now what I will be doing is, I will be writing something called results here. So what I will be doing is, you have two things now. You can just directly copy this here and paste this here, and just go to first HTML, submit this query. So it will take, okay, so select, okay, so spelling of the select was wrong. So yeah, you see here now I was having the error, and it actually showed here that error must be select statement. Okay, so it actually gave me this error here, and I saw that this is the error here. Okay, so everything was correct, but the spellings as usual. I'll submit this query again. So again we have some error here, incorrect syntax. So we have wrote something incorrect, which is actually a dot. We have written a dot somewhere. Okay. Where is the mistake? So let's get back to the first line. Okay, this is correct. So then okay, so the biggest mistake is, after each and every line we have to write a comma, which I forgot. So you have to separate them with the commas, because why we actually are writing a comma separated values, right? We actually are getting those as columns, right? So there must be comma for the separation. So yeah, I'll just fastly write it. It's just required for our first these box here. When you are writing here, there is no need to write comma after this. Okay, so I'll just submit this here. I'll see. Okay, so from gals back info as I, incorrect syntax near the word from. Let's see. Okay, so gal spec info as I. Let me make it clear. From gal spec info as I, gal spec line as L on I dot spec object id, spec object id. Okay, so it must not give error now. Okay, I'm just tired of it now. Actually I gave it this proper tab spacing, so now it must actually not show the error because it's taking time, right, to fetch 1000 galaxies. So it must not actually give the time error, sorry. So we'll just wait for few seconds. Alright, just rerun this now again. Till it's running, we can actually write a query and let's see which is fast. Okay, so we will write here, we will write a command here to fetch this query. So I'll just fastly write run is equals to sdss dot query dot query underscore sql, then query, and now if results. Now what I have to ensure that if there are results, if there are some values for the results, then you have to actually store that value as a CSV, that is table is equals to table result and table dot write. Then we have to just write the AGN underscore, let's say, data dot CSV format. We have to define, these are all the commands of the Astroquery. Okay, overwrite is allowed, and since I'll show you why overwrite is allowed, because we might have to added our first row of the table. Okay, so print RCSV, actually print saved, else print failed. Okay, so again, okay, so I just forgot to write a comma here. Okay, so what I will do is, since there were error in this thing here, I'll just go here and I'll just copy paste the command here, and okay, SJSS is not defined here. So because, okay, so we have not imported our things here. So import Astroquery. So this is how we have to import Astroquery dot SDSS. So when you are working with manga, you have to go Astroquery dot manga or ZFT if you have to go with the different things here. Okay, import SDSS, and from astropy dot tables import tables, and import pandas as PD, import no, from Galamo import BPT. Okay, so I'll run this data. So you see the kernel is busy now. So when you hover on this kernel button, you will see that it will show three things: kernel status busy, because it's running the code, and other thing is executed cell 0 out of 1. So the total cell to be executed is 1, and elapsed time is actually how much time it's taking. Right now it has taken 23 seconds. So till now, okay, so it says back gateway. So what I will do is I'll just try to. So you see, actually there was some error in the HTML there. So actually gave a 8 KB of data, and it's actually, I guess, okay. So there was some error here. Okay, okay. So there was an error here. Mm, maybe there might be some error with our code itself. So I have did something in SQL query. So what I will do is I'll just paste this earlier code of mine here for the convenience. Maybe there might be some syntax or kind of some spelling error somewhere. So yeah, there was some changes. Okay, so what I will do is I'll stop the kernel, interrupt the kernel here only. So you can, if you want to stop something, you can just go to kernel and interrupt this kernel, and I'll just rerun this code. Okay, so similarly here I will paste the code here. Okay, so I'll delete those parentheses or all those things here. So what I will do is now I'll submit this. So I'll see if this works. Yeah, this works. So you see the file size, it's 207 kbs, and while I open this, so you see we actually have this data here. Okay, so we have the plate ID. So earlier in the code I have actually extracted these, so these are not that much useful, but they are sometimes useful to get actually the exact uh, object. Okay, if you don't have the R and deck. Okay, so from HTSS only, then we have these flux and all these units, all these unit are way to sulfur 263. So you have to actually remove this first row here, because from for a basic sense, glamour work from the first row, which actually must be the columns names. Okay, not those added things. So similarly this must also work, so it's working here. So till then I'll just explain you what is the concept of BPT. So you have all these opens, right? When you will go to the first link here, so it's a very basic and very easy kind of explanation for a BPT diagram. Okay, that's it. A very small and a very crisp information about BPT diagram. So I'll just want you to guys read this for our time, and I'll just explain you. This is one of the BPT diagram. So we have different BPT diagrams here. So I will be showing you how these type of things vary. So basically, as of the perspective of a normal person, let's say, what do you think? AGN will have more oxygen kind of excitement, or a star forming one? Any guesses? So the excitement of the electrons in different elements will, let's say, here you have this diagram. When I go back, so we have these three diagrams. So let's say we talk about these oxygen here. So what do you think here? The excitement of the electron is that oxygen element up to the triplet. So what do you think, that must be greater in the AGNs or in the star forming galaxies? So there is actually the excitements, okay, of electrons. So they are exciting, so they are burning out. Okay, so what do you think? Any guesses? Any random guesses? So yeah, any random guesses? We have Deep, Prutha, Jashandeep, and then we have Rafal, Yashdeep, and Surpriya. So any random guesses? So okay, so I just want to know that oxygen triplet will be higher in AGNs or star forming. So you have to just get an idea of where the processes are more, or so you have to just think about it. Any guesses about that? So yeah, any guesses? Any random guesses will work. So yeah, any comments? So I want interaction, guys. Okay.
I think it may be more abundant the oxygen in when the star is formed than before being formed.
Yeah, but I agree with you that during the star formation there are very much metal rich. Even in the young galaxies, we have a metal rich quantity. The metallicity is high, but this time we are talking about their excitement. So when they are burning out, so I think it should be reverse. What I think is uh, there will be less metal when the AGN processes are going on. So it will be actually stopping star formation. It will be actually quenching the star formation. Don't you think about that?
So I maybe don't understand it.
Ah.
You are saying that when the star stop working, saying like that, uh, it's when the metal components start being more abundant.
Uh, I'm saying that when the star is formed or when are forming in star formation galaxies, I'm saying the metal components are more because those metal components are providing the stars to get more for the star formation actually in those galaxies. But when we consider about
Ah,
AGNs, uh, AGN actually are literally a kind of most powerful object in those galaxies, right? So however in the perfect classification we have blazars that I will be going to explain tomorrow. So however they are most powerful object of our universe. So that are the part of agents. So what they do is they quench the star formation. And what do you mean by quenching the star formation is they are actually uh, stopping or they are actually what we can say actually burning the metals. Okay, so there will be a very less metal rich properties there at that time of period. Okay, so you can say that in the old galaxies as well you will find very less metals, and in the galaxies we have the star formation, you will find more elements and less excitement. Okay, so that's what I want to say. So now we'll be looking at the plot. So just a second. Just a second, guys. Okay, so coming back to our work. Sorry for that delay. Okay. So now it actually we can't actually directly say that AGN will be having more doubly ionized oxygen, or star formation galaxies will have more or less. That is actually wrong, but sometime it's true. Okay, sometime it's true. Sometime, because what AGN do is it can actually increase the star formation and it can decrease the star formation also. So it varies in different cases. Okay, so just a second, let me. Okay, so now discussing about these ratios are actually very important, so that we can classify these things here. So basically this ratio, oxygen ionized oxygen by H beta, is actually the hardness of radiation field that is released by those galaxies. H beta is the recombination line from the hydrogen and trace the total number of ionizing photons. So you must write these things, or you must have an idea of these things, that H beta is the recombination line of hydrogen. You know guys these things. And oxygen this O3 at 5007 we actually got from our query, is actually the photon energetic enough to produce oxygen doublet. So these are the energy kind of W ionized oxygen, right? So that's the value of those fluxes. So therefore our low value of this ratio will be actually softer radiation field, and high value of this ratio will be actually the harder radiation field, right? So what AGN accretion disk produces extremely hard X-rays. Okay, so we get X-rays, and even from jets we get a radio hard. Basically from X-rays we get a hard X-rays, so which are actually dependent to produce much enough oxygen by H beta ratios. Okay, so these are why this is important. And here you see here in this on the x-axis you see nitrogen uh, 2 divided by H alpha, which is actually the metallicity and ionization conditions. So H alpha traces the hydrogen recombination, and the singly ionized nitrogen value come from these thing here. Nitrogen behave largely as a secondary element as to moderate to high metallicity. So as you can see these things vary here. So AGN actually also enhance AGN spectrum, also enhance the value of nitrogen doublet, nitrogen singlet here because of different ionization structures. So low value of these these ratio will be actually metal poor H2 region. Okay, and metal rich gas or AGN activity will produce high kind of these ratios. Okay, so this is the case here. Similarly we have the same thing for sulfur and oxygen here. Okay, so now what I will be trying to do is, since we have the data, so any doubt still here? So any doubts? Okay, okay, uh, so okay, it's still working. Okay, so what we will do is, I don't know, it should not take that much time. It's not that much big code. So I'll just refresh and restart and run all. However, we have already downloaded the data, but I want to show you here also. Just a second, it will hardly, it must hardly take 1 to 2 minutes actually. It's not a big query. We have just 1000 objects. So what I can do is, I can just go to this file here, and I'll just name it as AGN underscore data. And what I can do is, for you, I'll just drag it here, and I'll just write SGSS underscore SQL. So you will get an idea that we have not used Python here. Okay, so I just drop that in the same folder, and until this work, what I can do is I can make a new Python notebook for you guys, which will say Astroquery underscore bpt underscore analysis, let's say. So now we will be calling those things here. So I will be writing those Python packages. Import bpt from astropy is now not needed, so you have to just write one line here to plot a bpt diagram. Okay, so before that I just want to show you guys some things that which will be actually shown you from the main page of Calamo, which is actually a tutorial information. So when you will go to about, here you will see in the bpt I have written some of the information what we have used here. Okay, so actually we have made a pipeline which actually use these type of formulas which was given by Kaufman and Cooley in 2003 and 2001. So they are the very constant researchers in the field of AGNs. So they have given this ratio that if this uh, if the data come below this region, then there will be this classification, and if that come above that region, that will be some other classification. Okay, so if you want, you can just, okay, just a second, why give that error from Gelamo? It was just like that, I guess. What's happening? Okay, so it must not give that error. Which kernel I have chosen here? It's actually Gelamo. From astropy dot fits, import fits from Gelamo, import bpt. No module, I got the idea. Dot io, sorry. Okay, so there is some error here, which was, I guess, not. Okay, just a second, guys. I have to just see this. I think there is some error in our Python package. So just a second. So is it showing you the same error from Gelamo import bpt when you write just from Gelamo dot import bpt or not? Are you having the same error? Just tell me once, because I will get an idea so that I can fix it by tomorrow for you guys and we'll work. So till then I'll just explain you what we were supposed to do. So just type on your kernel your cell import glamos.bpt. So it might not give the error actually, because it was working file I actually used 2 day before. Okay, so okay, so you can actually, yeah, it's actually recommended because even the TensorFlow requires the lower version of NumPy and Pandas. So also it's not recommended to download the latest version of Python itself. So Python latest version doesn't support 12.12 version of TensorFlow, which was actually very useful. So but anyone other encountering that problem during this import or not? What I will do is just I'll cross this thing here. I'll relaunch my thing here. Oh, so the rest of part is very easy. Actually, we learned about the Astroquery. So rest of the part is very easy. Just we have to write one line for the whole classification. Okay, so we have a whole bunch of things there with us. Just a second. Uh, Guys, please respond. Jashandeep, Prutha, Deep, and others who have not the same error as Rafal, because Rafal was having the error for NumPy, so that's the different error. But the error must be similar to what I am getting. If I am getting this error, uh, then I think if you're getting the same error as mine, then there must be a problem with the Python package. But there should be not that problem, but might be there will be some TensorFlow problem, because TensorFlow change a lot from time to time. So yeah, so you have to just one line write one line and tell me if it is working for you guys or not. So yeah, okay, so let me change the kernel once. What I will do is I'll just change the kernel here. I'll just change my kernel from, let's say, this one, and restart. Okay, so just a second. Okay, so anyone getting the similar? I've installed the module, but it's still saying not found. Okay, so just a second. So it's installed, then there might be some error with your system. Like right now, I'm also getting the same error, but I have to refresh this thing. So after refresh, it will definitely work for me. What I will do is I'll just do one thing. Just a second, I'll just refresh it from here fastly. Okay, so let me see if now it's work. Otherwise, I'll just fix it by tomorrow and present it to you. That's not a big case. Just a second, why it's happening? Okay, so there are some, I can see there are some TensorFlow errors here in the pipeline. I'll just fix it by tomorrow, and I'll discuss it with you. So might be there's some update in the TensorFlow and which is not spotting it now. So what I can show you is I can just directly go to the tutorials here. So actually it was working 2 days back. I just checked it, or there might be some issues with my Jupyter notebook then. So what we will be going to do, we have the CSV file, right? So in the CSV file we just have to write one line of code with Galamo, which is bpt.draw and the CSV file name, and it will be directly show you the plot. That's it. For this one line, I don't know why it is giving this whole chunk of error to me for the TensorFlow. So there are some file missing. Maybe the new file for the TensorFlow has been uploaded there, so I have to just install those uh, requirements, I guess. So I'll just fix it by tomorrow and just show you this example. Otherwise you can just check it from here, that our BPT modules provide you 3 color maps, which is default one, this one, and then bubble and the soft one. And there are 4 formats to save the files, which is a PDF, PNG, SVG and EPS file. Okay, so for changing the map, you have to just write comma map is equal to bubble, and it will actually show you this beautiful, this is actually my favorite AGN format. So it will actually show you a very beautiful classification. You see here these are Cooley's and this is the Kaufman line, and after this line we have the AGN, and before that we have the star formation galaxy. Similarly, there is one more line here of separation which actually classifies Seifert's and Liner. So I will be explaining these are 2 different type of galaxy types in the AGNs only, and these are actually based upon their morphology as well as spectrum. So they have broad line and broad emission lines and narrow emission line. Based on that we classify these things. So I will be explaining to you tomorrow in very detail. So please don't miss the lecture on the AGNs, because that particular lecture will be focused and very much detailed in the field of AGNs. So what I have learned so far, I will be telling you every single thing in that lecture, and either I will be showing you through PPT, or I will be sharing my iPad screen and I will be writing it like a hand on notes with you guys. So yeah, so similarly we have these things here. So you can also have this color band here, color map here, and then similarly you just have to change the map. And how to save the file, you have to just choose the color map, or delete this command if you wanted it the default one, and then you have to write save fig is equal to true, and then output underscore file name, and then you have to write the file name and it will actually save the file. So there are some things that you will account. Let's say you just upload a wrong CSV, maybe you just delete one of these columns, okay, one of these columns, or rename these columns. It will actually give you an error that there is some this either okay, no such file or directory. Just a second. Basically if okay, so basically it must not give this error. Actually this is something else. I just want to show you something else. I just want to show you some different thing actually. Okay, I'll just tell you what it will be actually printing. This is actually, I guess, the older version. So basically if you remove these h beta line here, let's say you remove this column name here, okay, so it actually work on this particular names and exact values of these names. Like even if you write F capital, it won't work, because it is actually designed for SDSS classification for the optical spectrum data. So you have to just write it. Otherwise what it will be doing is the current model. So this is for the old model, I guess. So it will be actually giving you a error that you can either check the documentation, or either you can just fix those particular columns. So it will actually detect the column out of your CSV, and you it will actually show you the particular error or which column is missing in your code. Okay, so you can just fix that in the that case. So similarly, so yeah, this is one of the other query for just for example. So this is how the BPT work. It's very simple. You can just write this one line of code and you can get the classification. But actually, it's way more line of code. You see, you have these two basic formulas. Where it is gone on the main page. When I just show you the about section, you have these formulas. This is not just two formulas for the classification of the BPT, but these are only two basic formulas that you need to classify the galaxies. Then you have to apply different for loops for the classification, then different indexing from the those that will actually create a 200 bunch of line of code. Okay, so if I just show you the exact line of code that I wrote for the BPT module, you just have to go to github.com/glamo.org and you will see these profile. This was actually my earlier profile, which was actually not with me now, sadly. So but yeah, so these are some of the early contributors that worked with me in this repository. So yeah, so when you will go to the Galamo here in this particular thing here, oh wait a second, I'll just share the link with you. Okay, so I'll just fix this error, no worry. Tomorrow class will be more or less at this hour. Yeah, I'll just message you, but it will be at the same hours. So tomorrow I must be traveling back to my home city, so there might not be class in some case, but yeah, there will be definitely the class, but at the same or similar time. So yeah, so yeah, so when you will go to this link, I shared the link with you. Yeah, so you when you click on the bpt.py, you actually see the exact code written. So this is the function here, bpt.draw. So the you see how much line it is. It's not a single function, it's a multiple function, and it's actually the 312 lines of code that is actually compressed in just one line of code for you guys. So you see how much the Python packages, not only Galamo and other Python packages nowadays, help us to just concise a whole bunch of line of code, which is a journal code, to just single line or few lines of code. Okay, so you see these are whole chunk of data which actually write so much equations. So classify Seifert or liner, and these are the criteria for masking and all that stuff. So these are some of the complex equations. So you can actually read this if you want. So yeah, so this is actually the error. So basically, if the column are matched, it will print column match and it will give you the green sign. If the column are not matched, it will actually give you the error, that's check documentation or this website, or if there is a missing column or this thing or any required thing, it will actually print the proper error here, and it will help you actually correct the error. So this is all about those things I wanted to share with you today. So yeah, one more thing, just a second. So yeah, so however, before starting the next session, I'll make sure that you get the proper hand-on experience with Galamo, so no these type of error come. I'll just fix it tonight and I'll just publish a new update and I'll fix this issue. So yeah, you see it is a community project as well. Galamo is a community project, and just like AstroPy, if you find these type of issues, you can actually go to these issues here. Okay, so you can actually create a new issue and create the problem and describe the problem, so that all people can actually contribute to this library and we can improve this. So this is very basic library for the classification. So the other thing is, I just want to not only show you the BPT classification, uh, I also wanted to show you something very more, which is not possible again due to that error. Okay, so what I will do is, so we have actually made this something called galaxy morph. So galaxy morph is one of the other Python functions inside this. So basically it actually trained on these 10 basic labels, which are mergers, elliptical galaxies, spiral galaxies, and their further sub classifications. So we have used a custom CNN network to get an accuracy of around 98% now. So it actually work on this galaxy tree table, which actually follows each type of table, that if it is a round galaxy and which type of round galaxy it is, and if it is a disk galaxy, then which type of disk it has, and these type of classification to finally classify the galaxies, right? So we have used these different times. So you just, it is also just few lines of code. So you just, if you have a single image, you just have to write from Galamo import galaxy underscore morph as gm, and gm brackets, then you have to write the file path, and just it will process and actually give you this type of data, and also save it as csv, that galaxy with 95% accuracy and unbared loose spiral galaxy. So it will actually predict it. So it actually not meant for just a single galaxy, but you can definitely work on it. But if you have a bunch of galaxies, like bunch of galaxy data, it is actually highly resolution galaxy. So it our newer version, which is not actually published inside the packages, which I have shown you on the main website, you can actually use that version for the smaller galaxies, smaller faint galaxies of SDSS. So it is actually available for download here. So it is trained upon 17,736 more galaxies from decal survey, and you see we have like this uh, model is actually around 219 MBs. So it is most efficient model of Galamo yet, but we are working continuously to improve our structure and algorithm, so that we can provide much more to the astronomy community. So yeah, so these are some of the files. You can actually provide it just a table in which you have all the files. So it will actually took that file and give you the confidence, as well as the Skyger shaped smooth galaxy. Then we have merging galaxy. So this is actually a cipher type 2 galaxy that I will talk about tomorrow. And then I just uploaded a Apple image, so it actually gave 100% accuracy that it's not a galaxy. Similarly, we have galaxy, a barred spiral galaxy, so it will finally save the it as a CSV file. Okay, so you can actually write a comment. So actually it will predict, give you a table of this output, and you can finally actually save it as a CSV file. So gm.save CSV and results.csv your name. So it's actually similar to what astropy does here. So yeah, you see that these are very simple commands, nothing very much, but it the work it do is much more better. So similarly, if you find any issues uh, after tomorrow's class, when I will update this, and I'll just forward a message to you that you can just work on these tutorials again. So if you find the further issues or bugs, any bugs, you can just upload on the issues, and so that community and other people which are the part of Galamo can solve these issues. So yeah, so any query till here, I'll just turn off the recording still here. So I think you got an idea of how the structures work and how the classification of galaxies works. So more in the conceptual detail we will be working tomorrow, because this was not a very computationally heavy lecture today. So you got an idea of which type of libraries you have to use. So however, the most of important what we learned today was actually the SDSS query, from where you have to fetch the data. Okay, so any type of data, any type of analysis, you can actually plot those flux values in different type of values, not only BPT analysis but for more type of analysis, right? So maybe the flux variability data, all that data are stored there. So yeah.